Okay, I guess we'll start. So thanks everyone for attending today. We're very lucky today to have Olivia Carpenter-Lomax from Ricardo Energy Environment. So Olivia is a principal consultant. Olivia actually did her degree at the same time and in the same class as me at Durham University in new and renewable energy. And then she worked for a large utility before becoming a consultant. So she's going to talk to us about how we have to move beyond power systems in order to achieve anything with decarbonisation. Olivia is probably going to talk for about 40 minutes, and then we'll have some time for questions at the end. If you would like to ask a question, raise your hand in the participant box or type your question in the chat. Okay, so Olivia, if you proceed when ready.
Thank you, David. Thanks for the introduction. Hi, everyone. Thanks very much for joining. Let's talk about whole energy systems and in particular, moving beyond traditional power sector. So I know that David's just done an introduction of me, but just to give you a little bit more about my background. I did my degree in Durham in general engineering and specialising in new and renewable energy. And my first role from university was with E.ON, and I did a graduate scheme with E.ON. Like with many graduate schemes, that meant I could move around the organisation and get to know different parts of the organisation. So that meant that I got to be a power station engineer, which was great fun. I got to run around with a spanner and keep a power station running. I got to work in concentrated solar power for a bit, which was absolutely fascinating. And then more towards the end of my work at E.ON, I moved more into smart grids and smart homes and thinking much more about the customer side of the whole system. And then I made the switch to consultancy, and I now work for Ricardo Energy Environment. And Ricardo has engineers like me, but also geographers and environmental scientists and analysts. And my colleagues work in all sorts of exciting topics like water health and air quality and sustainable transport and sustainable economy. And of course, I work in energy and power. So we have an energy kind of part as well. And I do all sorts of projects from quite focused technical power network innovation projects right through to really broad future energy and future power systems projects, which I found really interesting. But one trend that I'm seeing, and really why I'm talking to you today, is increasingly my role is not just about power systems engineering, although that's kind of more of my background. It's becoming increasingly to do with different energy vectors and interfaces with other systems. And I have to consider points far beyond the technical as well. So societal and economic and environmental aspects, as well as just the technical. And I'm also a chartered member of the IET, and I'm on the Energy Sector Executive Panel. And the Energy Sector Executive Panel is as it sounds, it deals with the whole energy sector, which of course is beyond power in itself. And it also deals with a lot of interfaces with the other panels and the other sectors that we deal with in the IET. So transport and health and built environment and education. So all of those pieces working together. So that's another way in which I certainly am thinking beyond the power sector. So let's talk about whole systems and systems of systems. And these aren't new concepts, right? So it's not as if there's ever been a time where what happens on the demand side of the power system hasn't affected the rest of the system. And the gas and electricity systems, for example, have always interacted, sometimes positively and sometimes really quite destructively. But this has always been really on the fringe. And one of the points I want to make today is that particularly the drive for decarbonisation is really driving system of systems and whole systems as a much more pronounced and important and really vital part of what we do. So if we think about whole systems, the way we capture and convert energy is having to change. So we need to use more renewable sources, which are less dispatchable. And that's, of course, driving the need for flexibility elsewhere in the network. So suddenly our choice of how we capture our energy and how we manage that is being dealt with storage and with flexibility on demand side. And there's also the need for looking beyond technical. So because it's such a big change, we need to make sure we're changing technical alongside all the other aspects of the energy sector. So societal and commercial and regulatory and policy all need to change together. And these changes need to be agile and they need to work together well in order for the whole to be successful. And then system of systems. I don't know how common this phrase is, but it is just as it sounds, with different systems interacting and working together effectively and positively rather than against each other destructively. And of course, a good example of this is energy systems, distinct energy systems working together. So whether that's at different energy vectors or internationally with different energy systems in different countries. And as each region optimizes in their own way, making most of their own resources and their skills, they can then interact with each other to optimize a fully optimized whole and take advantage of each other's strong points. And then, of course, we've got interactions beyond the energy sector entirely. Just because energy is so pervasive, it impacts so much beyond just the technical disciplines within energy. So, for example, decarbonisation of transport obviously has a lot to do with energy because it's so much to do with energy efficiency and electrification and alternative fuels. And energy systems are increasingly reliant on communications as the energy systems get smarter and more connected. But of course, the communication systems are also wholly reliant on energy as well. And the built environment and utilities and leisure and health, all of these other sectors interact more and more with energy systems as decarbonisation drives change. So I'm going to talk about a couple of examples for us today, just to illustrate what my points here. As I've mentioned, I'm involved in a whole range of projects. Many of these are very focused on the power system, but even these, I'd say, we're increasingly looking at whole system and system of systems. So to do with, lots of them are to do with electric vehicles and demand-side flexibility and connected energy solutions and interacting with people and customers and other stakeholders outside of the traditional power sector. But increasingly, I'm also taking on projects that have this definite move away from the power sector, where really the majority of the project is focused outside of that traditional sector. So I'll talk you through a couple of example topics today. One is decarbonised heat, and the other one is low carbon shipping fuels. So let's start with decarbonised heat. And decarbonisation of domestic heating is a huge topic. It's one that is talked about a lot. And of course, if we were talking about retrofit, where the vast majority of the problem lies, then it's also technically quite complex because we have different buildings with very different characteristics and therefore very different solutions. But in this example, we're keeping it very simple. We're looking at new built homes up to modern technical specifications that are fully efficient, and they're furnished with electric low carbon heating options like heat pumps. And the question that we have to ask ourselves is what effect this has on the design of the power network, and therefore what does it cost, and what is the impact then on society, of all the relevant stakeholders, and of people living in those homes. So the first point here might not be a surprise to many of you. If you go from a house that has a gas heating system and you move towards an electric heating system, that house will require more electricity, and therefore if you're connecting that house to the grid, you'll need a bigger connection. that's pretty straightforward. And of course, on a whole development scale, you use the diversity in order to calculate how much bigger that connection is going to be, but it's going to be bigger. But the impact that actually has on the cost to connect is really dependent on site-specific aspects. So you might be connecting to a part of the network that has loads of remaining capacity, and actually the additional capacity that you need has almost no effect at all on the cost to connect. Or you might be connected to an area of the network that's highly constrained, and that additional capacity costs millions of pounds in order to release that capacity. And those are real examples from real anecdotes. So, so an important aspect for this then is, if those costs are more, if someone is paying, if the cost to connect is millions of pounds extra, who is paying for that, and how does that affect the cost of homes or renting? And actually the answer is not very straightforward. The most straightforward answer is really the main party responsible for paying for most direct connection costs is the developer. So whoever's developing these this development, these houses. And if we focus on private developers for now, they will generally build homes to sell and will try and sell those homes at the highest cost in order to make the highest profit. But the market price for those homes is set by the wider market, and we don't often decide to pay more for a home because it's cost more to connect to the DNO network. I mean, most people don't really even know what that means. So actually, it's unlikely that an increased cost to connect can be passed on to someone buying a house, not directly anyway. So really, that increased cost to connect gets absorbed into the profit margins of the developer. And really more likely, particularly if we're talking about large sums of money, the development simply wouldn't go ahead, or the design of the development will be adapted such that you'd avoid those large additional costs. And there are certainly examples of that where the number of homes have been reduced, or the specification of those homes have been reduced, just to get underneath that threshold to avoid those additional costs. But this picture is then made more complex by the use of ICPs and IDNOs. So for the vast majority of building developments, the contestable network infrastructure, so that is the new network infrastructure that isn't currently part of the DNO network, is built by an independent connections provider, an ICP, and then operated by an independent distribution network operator, an IDNO, rather than the DNO. And the main driving reason for this is because the ICP and IDNO offers a competitive price for the development, so the developer is likely to save money. And one of the main reasons for this is because an IDNO can offer an asset value for taking over the network. So that is a payment that the IDNO will make to the developer to offset the cost of developing the equipment in the first place, and that the IDNO then makes back through use of system charges to the connected customers. So for this reason, this really decouples the cost of developing the connection and the energy infrastructure for a development with the developer, and therefore the cost of the homes. Just to complete the story, of course, there are some proportion of costs that might be taken on by the DNO themselves. So that is if the infrastructure is not solely for the purpose of the development, it's a good rule of thumb that some proportion of them might well be taken on by the DNO, or if they're at a high enough voltage level. And those costs are then socialised. That means they're shared out amongst the DNO customers, which of course means that real people in society pay some of those costs, but it's shared out amongst so many people, no one will necessarily notice. So that just shows you how the picture of who actually takes on the additional cost and what the impact of those additional costs is really quite complex. I just think it's worth mentioning, though, that of course, if the cost of building houses becomes more expensive, then I would expect the cost of buying those houses and renting those houses would also become more expensive as a general rule. It's just that relationship isn't quite as direct as we might hope. So then finally, what technical solutions might help? And again, we're looking beyond the power sector here as well. So firstly, heating demand and the building fabric can't ever really be looked at separately. You have to combine them together and consider them as a whole. And of course, if you insulate your home more effectively and make it less leaky, then you can downsize the amount of the specification for your heating system, which then decreases the impact on the grid. Secondly, the design of the heating solution itself can do quite a lot to support connection with minimal impacts. So, for example, including smart controls that can really optimize the demand profile to the building itself can be really useful. And even just making sure it has a nice smooth ramp up without any spikes, so that we don't have to specify the connection in order to deal with any short-term spikes in load. And then, of course, there's an opportunity for demand-side flexibility, and particularly paired with smart controls. The two working together can be really beneficial and can do quite a lot to avoid the additional cost. And there are real cases where all of these are being considered at the very least to try and avoid additional cost for connection. But most insightful part of the story comes from far outside of even these issues and relate to the real world insights and barriers of the stakeholders involved. So I've got them here based on stakeholders, and these are just a few of them, but I thought it was worth mentioning them. Firstly, starting with housing developers. And housing development, as you'd probably guess, is a really well-established industry. And developers are used to building and selling homes in a certain way, including the certain technologies for heating. And they do this really well, and they do it really efficiently so that they can make a profit at the end of it. And this just means that they have really established supply chains for all of their equipment. They have established skills for all of their people and their contractors. They have established design approaches, so they design in a certain way. They have salespeople that know how to sell homes that look a certain way. The whole business is set up around them developing their homes in the way that they do. So it's this that has to change and adapt towards making what is quite a significant change in heating technologies. So it just means that they need to develop a thorough understanding. They need to start developing those supply chains. They need to train all of their people to design homes with this different technology, to install the different technology, to maintain and to sell homes with a different technology. And there's one really big point here, which is they also need to be assured that people will actually want to buy the homes once they're built, or rent them if they're building them to rent. But of course, that's what they're aiming to do. They're aiming to hand these homes on to people who will find them desirable and want to pay for them. And if they are to build these homes only to find that no one wants to buy them, then that's a huge risk for their company. On the DNOs, IDNOs, ICP side, so these are the group of people who design and build and operate networks. They need to consider how to optimize that design of networks when there is significant amounts of electric heat demand. And when we're talking about heat pumps, there just isn't that knowledge and understanding yet because we're so early in that journey. And at the moment, approaches to designing and connecting developments with lots of heat pumps are actually different depending on which organisation you talk to. And that means that from the point of view of developers or equipment manufacturers, they don't quite know what they're going to get, and they don't quite know how they're going to be treated when they're putting applications in or asking people to design networks for them. So that can be a real barrier to making this positive change. And then, of course, these parties being more and more aware of the smart grid solutions and how they can support with connecting and managing developments with high amounts of low carbon electric heat is really important. And as we go along the more general smart grid and DSO journey, this has to be a really core part of it. And the last one I've got on there is the homeowners, who of course is what this should be all about. And on the face of it, homeowners are going to be mostly concerned with if their heating works, is their home warm, and how much it's going to cost them to make it warm. But there are other points that are also really important. For example, the user interface. What is the experience like for the homeowner to use it, and how easy is it for them to use it well and in an optimized way? Because that a really well-designed user interface can be the difference between it being operated well and it being operated poorly and costing much more money and having a much bigger impact on the network. And user education might also be needed, and this might be quite a big societal change, because as a society we're used to the kinds of heating systems where which come on as you get home from work and take your cold house quite warm quite quickly, and that just might not be how we operate heating systems that use heat pumps in the future. And so there's actually quite an attitude change that we need to do, which is beyond the technical. So overall then, solutions really do need to take into account all of these things. We need a policy that supports change and is really informed by all of these perspectives, and incentivize the right behaviour in order to give the right outcomes. We need industries across different sectors working together. So that's of course power, but is also the building developments, the developments of developers of technology and solutions providers all need to work together in order to find optimized solutions that are really suitable for society, that are desirable and affordable and effective. And of course, we need to engage with real people to make sure that solutions are embraced and used well. So that's heating. The other example I want to talk to you about is low carbon shipping, particularly looking at developing countries. And the shipping sector is relatively hard to decarbonise. Yet existing fuels are really very dirty, so it's a really important project to take on. I've done quite a few projects in this general topic. Most of the projects I've done are looking at how decarbonised shipping fuels could be adopted in developing countries and the wider implications and the benefits that might have. So I thought I'd start with just an overview for those of you who don't know about some of the main zero carbon fuel options. And these are the ones that are based on renewable electricity. There are other ones, so biomass-based ones is a big category not covered here. But I just thought I'd give a quick run through of these. And if we start on the left with the simplest solutions, being renewable electricity and battery, but also the lowest energy density solutions. So there are lots of pros to just using renewable electricity in a battery in a ship that then can use a motor to get around. So some of the obvious ones are, we really know how to do this. So renewable electricity generation and networks to get that generated electricity around, and charging and batteries and motors are really well established technologies. But the major downside is that the energy density just isn't high enough for the vast majority of shipping applications. So only for the shortest journeys and the smallest ships can this really be used. Moving on one step then to green hydrogen, so that is using renewable electricity and 100% renewable electricity in electrolysis to produce hydrogen. And hydrogen is pretty fantastic. It is more energy dense than than our battery solution, which starts to solve some of those problems. And hydrogen is abundant and sustainable and non-toxic. It has lots of really positive points. It obviously has at least one major negative point, which is just how difficult it is to store and transport and move around, just because it either needs to be compressed in very high pressure tanks or cooled down to minus 250 or so degrees to liquefy it. So that's kind of the major downside, and there are solutions being developed, but they're not quite fully developed yet. If you take your green hydrogen and add nitrogen from the air, you can get green ammonia. So green ammonia is another step on again with energy density. So that means it is suitable for slightly larger ships doing slightly longer journeys. And it also has some other advantages over hydrogen in that it is easier to move about. It needs much less compression or much less cooling to move about in a similar way. So it's relatively easy to store, but it has a couple of downsides, mostly about being able to handle it. So particularly for developing countries, if you need specialist training to handle these fuels, then it kind of raises the bar of where you need to be as a country and as an industry in order to handle it safely. There's also quite significant energy requirements to generate, to create the ammonia. The last one on here is green methanol. And methanol is a carbon containing fuel. So obviously you need to take your green hydrogen and then get carbon from somewhere. So really the best ways of getting that carbon such that when you burn that fuel, you're not actually adding carbon to the atmosphere would be through carbon capture or potentially from seawater. So that does mean that you need to develop those supply chains and develop those industries a little bit further. And it just puts that extra requirement on being able to produce green methanol at scale. But once you do, it's pretty great. It's got a higher energy density even than green ammonia, and that means that it really is suitable for much more longer journeys and much heavier ships, and we're getting into really being able to replace traditional fossil fuels for shipping. So we've got lots of options there, and as I said, there are options beyond those on this slide. So how do we choose which zero carbon fuel we should be using? And this choice is dependent on quite a few factors. For example, the vessel type. So we've talked a little bit about how big the vessel is and how far that vessel is going, which will tell you how much energy you need to get there. And also the amount of storage available for the fuel is really important, and where you can store that fuel and how safely you can store that fuel. If you're carrying passengers, you might want to avoid ammonia, for example. And if you're going to run your ship on hydrogen, you might choose to store that hydrogen up the top rather than in the bowels of the ship, where it might accidentally leak and collect and potentially explode. Another point is the characteristics of the port. So if it's busy, what's the mix of vessel traffic it sees, and therefore what's the overall requirement for fuels across the whole port. The local resources is really important. So particularly if you're going to use one of these fuels on the screen, what is your local availability of renewable resources, and what does that look like compared to what's needed for your fuel? And equally, if you're using biomass-based fuels, what are your sources, and how sustainable are those sources? And then finally, we've got the global context, and this is particularly important for international vessels. So if you've got vessels that are traveling the whole world and they're stopping at lots of different ports, they really need to be assured that they're going to get access to the right decarbonised fuel in order to be able to get around. So if the whole world is adopting ammonia, then to a certain extent, everyone needs to be adopting ammonia. Of course, that's less the case if your vessels are staying very local. And it's possible that you might have different solutions for different vessel types. So we were starting to get into some of the stories about what adopting zero carbon fuels might look like. And stories are really powerful. So building a picture of what this could look like for you in your country can be the difference between a solution being taken on or it being ignored completely. So the most relevant story for electrofuels might be very different depending on the characteristics of each port and each country and each location. So to give, for example, ports could provide zero carbon refueling on busy shipping lanes. So bunkering ports are a thing at the moment where ships will come and bunker to fuel them on their longer journeys. But this might become more common because, as we've mentioned on the previous slide, lots of zero carbon shipping fuels have a lower energy density. So unless you're going to vastly increase the the fuel storage on these ships, they're going to have to bunker more often. So there's an opportunity for ports that are located on those busy shipping routes to locally produce green fuels and provide them for bunkering. And that can provide a really useful and valuable commodity that can be produced in that local area. The second one I'm going to mention here is that the adoption could be supported by demand from existing port activities. So where you've got really established routes, you've got ships that go between two or three ports on a really regular basis, or you've got ships that are supporting offshore facilities. You can use that existing and reliable demand for fuel to help support decarbonisation of your fuels. So you're creating your new fuels and you know you've got a demand for that. And you're not concerned that you're going to be creating fuels without a demand. And for ports that are reliant on trade of fossil fuels, which are really common, there are many ports in the world which are almost entirely trading in fossil fuels that are produced nearby. And of course, these locations are realistically heading for a decline. As the global demand for fossil fuel drops off, they're going to see a decline in demand for their commodity. And whilst this is great for global warming, fantastic, this has a really human cost. So for the people and whole communities nearby who rely on these industries for their livelihoods, we have to think about how we can support them and help them transition to a low carbon future. So if these ports can adapt to producing and exporting green electrofuels, or potentially serving as a bunkering stop, then this can provide a real new lease of life for these ports and support the communities. Another really important part of the story is spillover benefits. So that is benefits that are felt beyond the ports and the shipping sector themselves, in the wider communities and the wider country. And spillover decarbonisation benefits quite often are an important part of that overall story that can become really persuasive. So, for example, if we're establishing renewable generation at scale to support decarbonised shipping, then that means that you're developing supply chains and the economies of scales and skills to build and operate this kind of equipment to generate renewable electricity. And that then, of course, can pave the way to supporting development of greener domestic electricity supplies. And of course, generation of shipping fuels can be a flexible demand that can take up additional intermittent generation that can mean that local renewable generation does not need to be constrained. Green electrofuels and green hydrogen can also be used in other industries, like heavy land transport can be fueled by green electrofuels, or green hydrogen can be used to decarbonise industries like steel. So these spillover benefits can be a really important part of the story. But unfortunately, it's not all about finding benefits. The application of zero carbon shipping fuels needs real careful consideration about a whole range of aspects, and many of these are not black and white. So firstly, it's really important to understand the local context. So how supportive is the local government to develop decarbonisation, to install renewable generation? What are the regulatory requirements that you have to adhere to? What does the electricity system look like? Who owns what? And how is it managed? All of these aspects are really important to consider if you're going to develop a solution that's going to work. And what if we're talking about a country where the local community doesn't have reliable access to electricity at all? So is it really appropriate to generate renewable electricity to decarbonise shipping when local hospitals don't have power to refrigerate their drugs and vaccines, and local school children have to do their homework by candlelight? Generally, our approach is that renewables for decarbonisation of shipping should not be at the expense of providing electricity access to the community, or of decarbonisation of the wider grid. So we talk about building renewable generation in addition to that is already needed for these wider goals. And sustainable responsible renewable generation is all about considering the wider environmental and social impacts of establishing renewables. So, for example, if you're cutting down virgin rainforest in order to build solar plants, the negatives might outweigh the good in those cases. And equally, if you're building renewable generation on land that would otherwise be used as agriculture in order to feed the population, again, the societal costs might be too high. So these aspects really need to be considered when we're designing solutions. And I've mentioned this a little bit already, but around the world, there are millions of people whose lives and livelihoods rely on declining industries and fossil fuel industries. So if we're talking about replacing those industries, we really do need to consider this. If societies are going to be persuaded that they should give up these industries in favour of greener options, we should be thinking about providing roles for people of all skill levels, and the means of accessing those roles, so training or relocation or whatever's necessary to provide access and to support that transition in a way that is really effective and appropriate for the people involved. And all of these aspects really come into play when thinking about what might be the best story to build around support for electric fuels. But this story might lie far outside of traditional energy and power sector. So just to give a bit of context, just yesterday I happened to be in a call with a set of in-country stakeholders in a developing country, and they were getting really excited about adopting electrofuels and decarbonisation of shipping, which is fantastic. But of course, they were all shipping people. And we had one person speak up and say, this is really great, but actually the wider decision makers in my country, they are not going to get excited about this. You need to link it to decarbonisation of mining, to creating green jobs to wider societal goals. And only then is it really going to be taken on board, because actually just presenting a technical solution is not going to get the job done. So as it happens, just yesterday, I have an example of how important these kind of aspects are. So I have a few concluding messages for you. Firstly, that the energy system solutions and this whole energy system solution should be designed to meet the needs of society, not simply to keep itself operational. Every time we should be going back to what is right for society, and what is right for society both now and in the future. And of course, that means that energy systems need to be agile and flexible so that they can change to adapt to risks that are emerging, and also opportunities, new business models and new technologies and new ways of doing things. The energy system needs to be whole system, as we've talked about, considering energy from source to use and across technical and societal, commercial and regulatory and policy backgrounds, and work within this system of systems. So interacting between energy systems and with other sectors, with systems working together really effectively rather than against each other destructively. And solutions fail if they don't consider this wider picture. Sometimes success is dependent on being able to tell the right story and taking all of these aspects into account. And many of these solutions are not one size fits all, and that's something that I particularly find on a global scale, with different geographies and legacy infrastructure and resources and cultures. And there are compromises, and there will need to be compromises, and the solution is not always black and white. But we should design solutions for the future we want, and that picture of future should be with a whole system, multifaceted system of systems view, and should really put society at the heart of what's needed, and have considerations far beyond the power sector. So I'm going to finish there. Thank you very much for listening. And if you spotted the point on my first slide that I should no longer call myself a power systems engineer, I tend to go with future energy systems engineer now, although it changes depending on who I'm talking to. Thanks, everyone.
Okay, yeah, thank you very much, Olivia. That was, well, I think I found that extremely thought-provoking because of the sheer kind of breadth and depth of all the different things you're prepared to take into account, which I think here in academia, we can sometimes avoid thinking about a lot of those things, even if we are claiming that we are taking a whole systems approach. If you have any questions for Olivia, please either put them in the chat or raise your hand, and then you can speak. I have a couple of questions. So my first question is, it kind of relates to what I just said, which is, I think it's fine to conceptually say we need to account for everything, but I think realistically, you can't do that. So you have to draw some, coming from thermodynamics, draw some boundary around your system and say, this is the edge. Like, do you do that? And if so, how do you decide what the boundary of the system you're actually considering is?
It depends on the project. So I have colleagues that do the sorry, words escape me. I have colleagues that do the kind of whole life cycle analysis, which is fascinating because, of course, whole life cycle analysis in its true form really takes absolutely everything into account when you're assessing something. So I look to them when I'm talking about drawing boundaries, because I think they've taken it down to an art. For us, it depends on the project. Quite often, we will be in the position of our project scope not really taking lots of these things into account. So what we will do is we will flag them and raise them, and make sure that they're considered next time. And quite often it means that whoever it is that we're delivering the project for, quite often policymakers or network operators and those kinds of people we work for, they can go away and make sure that they're taken into account.
Okay, yeah, that's a good answer, thank you. Chris Mullen has a question.
Hi, Olivia, thanks. That was really interesting. I'm just wondering, and you might not be able to talk about this, but can you kind of describe some of the things you do in an actual project, and what sort of people you're working with, just a sort of more I don't know, grounded in a bit of context. I'd be interested in that.
Sure, I guess a day in the life type thing. I do a really wide range of projects. So I do some projects which are...
I'm particularly interested in the low carbon shipping.
Okay, that's a good one for me to talk about. So I've done a few of these recently, but the one that's published, so I can talk about, is one that we did for one for Ocean Conservancy, which is an organisation over in the US, and we did that based on various case studies in South and Central America. So there is a published report, and what we did there was we looked at for various countries in South and Central America, we understood policy context, we understood geography, we did studies to look at real usable renewable potential, which is kind of the power engineering side of it, of renewable generation. And we also engaged with in-country stakeholders to talk about the real practicalities of what these vessels are used for, what does decarbonisation of these vessels mean, what does transition from a really established way of doing things in ships that last for decades, transitioning that to zero carbon, what does that mean and what does that look like? So at the moment there's one report published on that, which takes 4 case studies to get into that detail and talks about those case studies in detail, but also talks about how those case studies apply to other places. Because of course the idea is not to solve it for one port, but to solve it for many. And then there's potential that project could go on, and I'm actually just starting a follow on for that project now. I don't know if that helps, hopefully.
Yeah, that does, thanks. Is presumably that report's on the Ricardo website somewhere, is it?
It will be. I don't know if do we have the ability to send out links, David?
Yeah, absolutely.
I'll send you a link.
Oh, thanks very much. If I can take another question, you mentioned whole systems thinking and systems of systems. Mm-hmm. Do you see those as various separate things, or do they overlap, or how are they different?
They hugely overlap. I think if we were genuinely whole systems, it's a conversation I have quite a lot in my role in the IET, actually, because as the Energy Sector Committee, there's a real question about where do you stop talking about energy, and if you're talking about decarbonisation of shipping using decarbonised fuels, is that energy sector, or should we be talking about the transport people at that point? So yes, I think they overlap massively. I think if we were being truly whole systems on a global scale, we would basically include all of human action in the energy system. But of course, we need to put boundaries on it, going back to the question that David asked. The way I look at it is if we consider the power sector is as a system, that system has to be whole system, in that you need to look at right from generation to use and all of the different aspects and different technologies, and also the different layers, so customer, organizational policy, all of the different layers and transactional and all the things that need to work to make that happen is as a system. But that system inevitably interacts with the power system in France and also the transport system in the UK. And if we have issues in one, then we have issues in the other. So I think whole system would be that whole power system to me. And then system assistance would be the interactions with the other things.
Yeah, that's a good way to think of it. Thanks. Thank you.
Okay, we've got a question in the chat from Matt. So Matt says, thank you for the very interesting talk. On the topic of heat decarbonisation, can you tell us a bit more about how DSR and more generally smart solutions might work in a real system for reducing the network connection for a development? Would a DNO really consider this as a way to reduce the demand required by a network generally without some kind of guarantees of performance? Or might they need some sort of performance guarantee, e.g. in France where there's a lot of electric heating? As I understand, the power in your house will trip if you go above some kilowatt level.
Yeah, so it's a really good question. And I think part of it comes back to what I mentioned about the need for just a build up of confidence, because of course we're all free to use all of the appliances in our homes all at once and get all our neighbours to do exactly the same, but we don't, and the DNOs are confident that we don't, and therefore they designed the system around us not doing that. And because this is a slightly new scary way of doing things, that confidence isn't there. And of course the network operators are very intentionally a risk-averse organisation and sector, and that is just so that we can keep the lights on, and we have such a reliable power system for that reason. But it does mean that I think probably at first they probably will need some reassurance. But I do know of a case where there is real discussions going on about managing both low carbon heat and electric vehicles in such a way to directly mitigate the need for connections costs, and doing that through smart solutions. So effectively a local DSO type solution on the very large development that's being developed. That is in discussion, so I don't know if it's going to happen, but that is in GB, and the DNO is involved in that. So it's, I think, probably just around the corner, and I'm hoping that in 20 years' time, we'll do it as a matter of course and wonder what all the fuss was about once we get that understanding up, and we really develop that thinking. But there's just this transition where we have to collect that information and understanding and work out how to best optimize the systems.
Yeah, I'll just add, so we specifically have a project that I run with Northern Power Grid where we're looking at how you value different smart solutions for like exactly this, accommodating extra demand. And actually it's interesting because in some ways the DNO is very risk averse, but in other ways they're kind of not, because they said, oh, well, if we contracted for a megawatt of demand response, we would assume that we could get an extra megawatt of demand. But our simulation results show that it's actually quite a lot less than that because of like where it is in the network and the fact it's not totally reliable and the fact it might not always do what you want. So yeah, building that confidence is difficult, but also you need to build kind of more realistic expectations into things that people don't necessarily fully understand yet. Okay, do we have any more questions? I think someone has put a link to one of the reports on zero carbon for shipping in the chat here.
That looks like it's probably the right one.
That's probably the right one. Excellent. So if there are no more questions, I guess we'll end this pretty much on time. Matt, we have another talk in 2 weeks, don't we?
Yeah, that's right. In 2 weeks, we got Stefan Fenninger from ETH/UX. He's moving to U Delft, talking about Calliope. The exact title I don't have to hand, but it's on Calliope, and that's his tool that he's developed over a couple of years, and it should be super interesting.
Okay, That's good. So yeah, thank you very much, Olivia, for giving the talk. Thank you to everyone else for attending. Oh yeah, this will probably end up on the Supergen Energy Network's YouTube channel. So if you would like us to not put you attending this meeting on there, please let us know. But I think most people didn't speak, so it's probably okay. Okay, yeah, good. Thank you very much, everyone, and we'll see you in 2 weeks.